Hello and welcome back from our break. For this module, we're going to be talking about objects and types. So we've actually already seen some objects, as we'll find out. Our agenda for this module is we're first going to introduce objects, talk about some of their fundamental properties. We're then going to introduce classes. We're going to go a bit slowly at first just to try and make sure we all understand the important details of them. We're going to talk about initialization for a little bit, different ways to initialize things in C++. We'll then cover encapsulation and how class types enable us to do that. And then finally, we'll talk a bit more about the const keyword and how it mixes in with objects. So first, objects. What is an object? Well, it turns out we've already seen some. So here is a little program, and we see we've just got two integer local variables. Both of these are of type integer, so integer int is their type, and we've initialized x with 1 and y with 2. So this doesn't look very exciting, but we can actually learn a lot about C++ just from this little example. So one of the most important features of C++ is that it has a lot of high-level language features. Like it has functions, it has control flow statements, it has variables with types that restrict how we use them. But with all these high-level features, the language is defined in such a way that it's easy to map all of this code to real hardware. So the compiler can take all of this high-level abstract code that we've written and burn through dozens of layers of abstraction in some cases, inlining, taking functions and combining them together when it makes sense, or getting rid of whole dead code blocks. So the compiler is able to do this and map it to extremely fast code that runs on modern CPUs. So as a part of this, an object. So I guess the first thing that's important to say is that even types are a high-level feature. So there are no ints in memory. Like if you look at memory, it's just a giant array of bytes. So here might be our model of what memory looks like. It's just a chunk of space. And an object is just a region of storage. So it's an array of bytes somewhere that has a type, and we use that type to tell the compiler how we want to interpret that memory. So for example, our object x might be sitting in these bytes in memory, and our object y might be sitting in these bytes over here. But the important thing is that it's just memory. It's just this array of memory. It's just a piece of memory. It's also important to note that x and y are completely different, so they occupy completely different pieces of memory. So what we're really saying when we declare a local variable is, hey, when this function f is called, I need to please compiler and computer make sure that there's some space in memory to hold these. And the actual mechanics of how that works you can find out in a good C++ book or another course. We won't go into too much detail there. It's just the important thing is that they're here. So what else can we learn? So we know that x and y are objects. They both have a type, int. What else can we learn about them? So another important thing is that of object lifetime. So we've discussed scope a bit already. We've discussed that the scope of x is from the point it's declared to the end of the function, and the scope of y is from the point it's declared until the end of the function as well. Closely related to this, at least for local variables, is what's called lifetime. So the variable x comes into existence when it's declared, and it goes out of existence at the end of the block in which it's declared. And the same is true for y. Now, an important thing to note here is that the objects go out of existence in reverse order in which they come into existence. So x comes into existence first, it shows up first, and then y comes into existence later. And then at the end of the function, y is basically what we'll say later, it's destroyed, it goes out of existence, it ceases to exist, and then x. So we can't use variables before they exist, and we can't use them after they exist. For local variables like this, it's obvious that we can't do that. Like there is no way, the compiler won't let us. But we'll see in the next in 2 modules that there's other kinds of objects where you might run into trouble. So beyond that, there's a couple more things we can learn about objects. The first is what's called copying. So let's say that we have a local variable x, like we had before, but then when we initialize y, we initialize it from x. So basically, we're taking the value of x and we're using that value to initialize y. This is called copying. Now, it's not any different for integer, for ints or built-in fundamental types than normal initialization, but it's semantically important for class types, and we'll see why later. So conceptually, we can say, okay, this is copying. Now, it's important to note this is distinct from assignment. So assignment is where you have two objects already, or you have one object and a value, and you assign from the value of one object or a value to the object on the other side. So this is what we call assignment. So the difference is whether or not there is whether or not you're initializing a new variable, in which case it's called copying, or you're changing the value of an existing variable, in which case it's called assignment. So that's basically all that we need to know about objects. Like, these are the fundamental things that we need to know about objects. Every object is just a region of storage, some bytes in memory. It has a type that tells us how we can use the objects. So for our integers, they're just we're able to do integer things with them, like add them, subtract them, compare them, but we can't do things like append to them like we could with the string, because there's no notion of appending to an integer. And they can be initialized, and they exist. Their lifetime is between when they are initialized and when they go out of scope, at least for automatic objects, local variables like we've seen so far. And they can be copied and assigned, and the distinction between those we'll see a bit later. So if we only had fundamental types to deal with, that would be rather boring. Like, we don't want to have to write a program with just ints. And so classes enable us to compose more complex types. So let's start thinking about it. So let's start by thinking about a rectangle. So let's say we want to represent a rectangle in our code, and we want to do so by representing it using its width and its height. We'll ignore things like its orientation and its color is not important for this particular example. How might we do this in code? Well, we could start off and just say, oh, well, we have a rectangle width and a rectangle height. This is straightforward, but it's not very convenient. If we wanted to return a rectangle from a function, we'd have a hard time because you can only return one object from a function, and here we have a rectangle represented by two objects, the width and the height. Similarly, if we wanted to pass a rectangle to a function, we would have to pass it via two different parameters because we have we're again representing it by two objects. So this is where classes are useful, this is where they start to become useful, is they enable us to group like data together, group things into easier to manage chunks. So here is a rectangle class. So it starts off with the keyword class. So the class it introduces, this is a class type. Inside we use the keyword public, which means it's accessible to code that wants to use it. And we'll discuss this a bit more later in this module. And then we just declare two local variables, so a width and a height. This means that every instance of a rectangle will have a width and a height. Something that is important to note is that the class definition ends with a semicolon. This is for legacy reasons. You just have to do it. There's no really important reason why anymore. So if we want to use this rectangle, we can use it much like we did our two variables. We would declare a single local variable of type rectangle, and then we can access its members using the dot operator. So this dot operator says, take this object and access this member of it. So we assign the width to be 3 and the height to be 4. So what does this look like in memory? Well, it looks a lot like we would expect. So we have in memory, we need to store a width for our rectangle, and we need to store a height for our rectangle. And so each of these exist in memory. They'll be sitting next to each other. The compiler, might put them, a little bit apart or whatever. But the important thing is that the small rectangle itself is also an object. So rectangle is an object type, and it consists of these smaller pieces. So this is effectively any time we're building new user types, which are using classes, we're just combining smaller types or more basic types like ints and floats and doubles into a larger whole. But it's still just a region of storage. It's still just memory. So now that we've taken a look at classes, we should take a look at initialization and how we initialize local variables. So we've seen using the braces so far, but now we're going to, I guess, go into a bit more detail to show how initialization works. So first, the most important thing to note is that local variables are not initialized by default. So for example, here we have int x and it has no initializer. This is totally valid, like this code would compile and run. And many people expect that x has the value 0. X does not necessarily have the value 0. X has a garbage value. It is basically left uninitialized because we have not provided an initializer. The Visual Studio debugger does something very helpful here. If you're running a debug build of your program, it actually fills everything in with a special byte pattern, which we'll see in an example, and that way it makes it easy to detect when you have uninitialized variables and you accidentally forgot to initialize something. So the same thing applies to our rectangle type. If we have a rectangle without an initializer, it's going to have a garbage width and height, like there'll just be some random value. So we can initialize them both. We can initialize them using the brace syntax that we had before. For x, of course, there's just a single integer, so we use 1. For a small rectangle, we have a width and a height, so we have to provide 2 values, a width and a height. And if we had 20 members, we could provide 20 initializers in there. But generally, if you have more than a few, you'll want to better encapsulate your data, and we'll see how to do that shortly. So oftentimes, you may want to, default provide, just initialize it to a default value. So for int, you'll want it to be 0, or for a rectangle, we want a rectangle with a 0 width and height. I don't know why you'd want that, but you might. And this is a very common thing to want to do. So of course, we could initialize it by providing zeros for these initializers, but instead, C++ provides another way to do this, if you'd like. It's a bit terser and more consistent, because you can use it for any type. And you can just put an empty pair of braces. And what this will do is it'll just initialize something to its default value. So for int x, it'll be a 0. For our rectangle, it'll have a width and a height of 0. If we had a string is a little special, and we'll talk about that a bit later. But if we had a string, this would initialize it to an empty string. So it's basically the default value for the type. So to summarize, we can leave something uninitialized, but please don't do this. Like, make sure you initialize all of your local variables. We can do what's called, the technical term for this is value initialization, so we can initialize it to have its default values. We can provide specific initializers in order to initialize the object, or like we did before, we can value initialize it, and then we can assign new values to the members. So at this point, I'm going to turn it over to Kate, who's going to show us a little demo involving initializers.
You may recognize this code. It's pretty much what you just saw. And I've put some integers into the code as well because we really want to draw that parallel. It's not different for fundamental types and for user-defined types. You can see that rectangle is in this different color blue. It's not the same color blue as int, but it sure isn't the black of the other words in the application. And this is actually Visual Studio letting me know that rectangle is a type that we've defined.
The string type in the previous example had that same color.
Exactly. User-defined types are in that color. But by default, you can change everything in Visual Studio, but we've not changed those sorts of things. Rectangle is declared in the header file that you see being brought in here, rectangle.h. And I could right-click this and open header file, or I could double-click over in Solution Explorer. And there's that class statement that you saw on the slides before, declaring the rectangle class. The first line here, pragma once, I'm not going to hide that it's there, but I'm also not going to explain it. It's got to do with what happens in large projects. So here's 3 integers being declared: uninitialized, default initialized, and initialized with a value. And so hopefully that won't surprise anyone what happens when we come through this in the debugger. X is just looks like junk. Y is 0, and Z is 1. I should say Z, shouldn't I?
Yeah, I think so.
I'm going to say Z. See how you can spot Canadians passing so well, and then suddenly I say Z.
So that X, that's a kind of a weird value. Is that?
It is, isn't it?
We'd expect?
When I actually recognize this number, but it's much easier to recognize if I ask the debugger to show it to me in hex. That's a noticeable number. And in fact, you see it all over the place. because this is what the debugger sets uninitialized variables to. And that helps it to spot when you then try to work with them when you didn't deliberately set them to anything. So this is bad, right? Don't ever do this, please, but I'll show you what happens if you do, which is that each of the elements of the rectangle become themselves uninitialized. And then in a release build, it would literally be whatever used to be in the memory, which is pretty awful. Whereas with the value, if I hover over this rectangle and the debugger will show me the pieces of it, they both become 0. Or if I've passed things in, they become 2 and 3. Each rectangle has its own piece of memory. Here I'm changing the width and then the height only of the rectangle called value. So when I step over, you can see that value is now width of 2, height is still 0. Aggregate is unchanged. It's still a height of 2 and 3, and uninitialized is still its random numbers. We don't go and change all the rectangles, only the one that comes before the dot operator. So we change the width of value, and then we change the height of value. And in this way, rectangle is really just a container at this point, a way of holding a couple of integers to make them simpler to work with. We're going to make rectangle better in the demos to come.
Absolutely. So for integers, like there's no behavior to control. Like you would never want to customize the behavior for what happens when you try and initialize an int. But the same is not true for class types. Oftentimes we want to do certain initialization for our type, and we do so using what's called a constructor. So a constructor is a special function, and we'll actually go into this a bit more detail in the next section. But it doesn't return anything, but it's called automatically whenever you declare a local variable of a class type. And you can use it to initialize the members. So for example, this would be what a constructor would look like for our rectangle class. This would be a default constructor that initializes the width and the height to 1. And we'll see how this works a bit in the next section. So in this lesson, we're going to talk about encapsulation. So we don't usually want to expose our data members for people to just change willy-nilly. That, in general, turns out very badly, especially if you have large objects or objects that are composed into large pieces. It's also problematic in any large project. You want to constrain access to things as much as possible. It's not a security thing. It's just it helps you to write correct code and understand code when you're debugging. So let's first talk about what encapsulation is. So let's say we wanted to write a function that computes the area of a rectangle. So we could do this quite easily. We can write a function named compute area that takes a rectangle and multiplies the width by the height. And then we can see how we can call that to compute the area, and this works quite well. Like there's nothing particularly wrong with this. But the area is a rather fundamental property of a rectangle. So it'd be really nice if we could say this is a special property of each rectangle, and so we want to express that in our code. So we can do that using what's called a member function. In some languages, this is called a method. They're basically the same thing. In C++, we just use the term member function. So here's how we would define such a member function. It goes in the body of the class rectangle, and we can say int get area, so it looks just like a normal function. And this member function, though, has access to a special parameter called this. So you don't have to declare this anywhere. It's automatically declared by the compiler. And what that means is this is the object on which the member function was called. So for example, if you look over at our function f, you can see that we've called getArea on this rectangle named a rectangle. So inside of getArea, this is what's called a pointer, and we'll see more information on that later. So it's basically a rectangle. It's the rectangle there in the function on which we called the function. So we can use the this pointer and this arrow operator, both of which we'll describe later, to access the members of the class. Now, this keyword is not necessarily required. In most cases, you don't need to use it. It's a good idea to use a different naming convention for member variables and non-member variables. That way you can distinguish between them. And so if it's unambiguous what _width is, you can remove the this. And so you can just say width and height. And most people don't use this in their actual code.
That's why you started those member variables with underscores, right? So that you could easily tell them apart from locals.
That is correct. And there's many different naming conventions. So underscore in front, underscore behind, M underscore is common in some code bases. There's how you name your variables is entirely up to you, as long as you're consistent and have, it makes sense to you. So one of the most important pieces, one of the most important reasons to use classes is that we can use member functions to hide the data that they represent. So for example, we don't want people to be able to change the values of width and height willy-nilly. We'd rather, perhaps we'd like to have a resize function that allows us to do some checking to make sure that they're not negative numbers being passed in or something like that. So first, we'll need a way for people to be able to get access to the width and the height. And we can do that just by writing other member functions. So here we've written a getWidth and a getHeight, and they just return the width and height. Now, you'll see that we've made the width and height private. So the private corresponds to the public, and what public means is that you can use these from outside of the class. So in our function f that we had before, we can call getArea and getWidth and getHeight, but we can't access underscore width and height. We'll get a compiler error if we do that. For example here, those won't work. But we can access all of the public members, so we can easily call getWidth and getHeight. No problem. Compiler will be very happy with us. So this is all well and good, but what happens is I have two slides with the same contents. What happens if we want to initialize our rectangle now? Well, we can't access the underscore width and height, so we can no longer use the initialization form where we have two different, where we initialize them separately. We can still do value initialization because we don't actually refer to the members. But we can't actually initialize them to like a rectangle with the dimensions of 2 and 3. So what we can do is we can add a resize function. So, this resize function can take a new width and a new height and assign new values to the members. And then in our function f, we can just create a value initialized rectangle. So it starts off with width and height of 0. And then we can resize it to that size. But this isn't really great, right? I mean, we'd really like to be able to initialize things to their value. This would prevent us from making the rectangle const, because as you can see, we're changing it after we declare it. So ideally, we'd like to be able to initialize something at the beginning. And the way we do that is using constructors. So here, for example, I've written two constructors for the rectangle class, and I've gotten rid of the get functions just for brevity. So you can see here we have two constructors. We have one that default initializes the rectangle to have a width and height of 0. Then we have one that takes a width and a height and initializes the width and height with those. And so we are now able to initialize our rectangle using all the same forms that we were before. We can value initialize it still, which will end up invoking the default constructor. We can initialize it using the two explicit width and height, and that is done. It has the same result as before, but it ends up calling our constructor instead. And similarly, if we really wanted to, we could value initialize a rectangle and then resize it to the dimensions that we want. So why do this? Clearly this is a lot more work, having to write these constructors and accessors and other things than instead of just, accessing the member variables directly. But again, as we said, we want to restrict how we use types as much as possible. We want to make it easy to use them correctly, which means providing as few operations as are required. We don't want to make them hard to use. We want to make them easy to use correctly.
I often say that it saves people from having to remember. If we're writing a banking system and you had to say, remember, after you reduce anybody's balance, also charge them a service charge. And with encapsulation, you could say, I'm not going to let you get directly to balance. I'll let you call a withdraw function. And withdraw will charge a service charge. And now whoever's working with the bank account doesn't have to remember to make that call. Yeah.
And like back here with our rectangle, our resize function has made it impossible to change the width without the height. So we have to change them both at the same time. So we might also, we might change our resize function, for example, to check to make sure that the area of the rectangle is not more than 10,000. And by requiring us to provide a width and a height, it allows you to resize it more easily.
Right. So we can start to implement our business logic. We're giving you very simple classes today. They don't really have any business logic, but you're going to write real classes that do and that need to be kept consistent and kept sensible. And encapsulation is really the key to letting that happen. I've got some sample code to show you here, which is essentially the code that you saw from the slide. And if I run this application, and we can step through, it's going to be a little different now because in rectangle.h, we've implemented these constructors. So this is the default constructor. And just to prove a point, I decided to have it initialize the width and the height to 1 rather than to 0. I actually don't think I would do this in real life, but I wanted to prove that this constructor's code is actually being used.
Do we have to provide a default constructor at all?
No, but then people can't default construct your objects. Yeah. So if I comment this guy out, then the lines that are trying to use the default constructor won't work. This is the constructor who takes parameters and uses them, gives initial width to width and initial height to height. And you know the compiler doesn't read your words. If you want to foolishly put the width in the height and the height in the width, you'll just have a bug. It's your friend, but it's not that much of your friend. And there's the resize function, again, that uses those parameters. So if I step through here, our uninitialized variable is now not full of the special signal value. It's used the default constructor. However, just because the compiler will do this for you, I still don't want you to ever do this. I want you to do this with the open and close brace, because that really says to everyone who's reading your code, hi, I'm using the default constructor here. It makes it really obvious what's happening. So value will also come out with a width and a height of 1, as you can see down here in the locals window. Then aggregate will come out with 4 and 7. I can call resize on value, and obviously that doesn't change the size of uninitialized or aggregate. I can call resize on aggregate. Oh, I stepped into. I meant to do that. You can watch this here. The new width comes in as 1, the new height is 2. Currently here are the old values. And then after we step through,
it's worth noting that in the locals window here, you can actually see the this object, so it's the object on which we're currently executing.
That's true. This is always there for us, and here you can see it and what it points to as well. So then we change the width and the height to the new values. We come out, and we're back in our main code. And we've resized both rectangles. And now we can call this area function and independently get the area of the two rectangles. There's no relationship between them. They just both happen to be rectangles. Any more than if I have I and j are both integers, changing one does nothing to the other, and value and aggregate are separate rectangles here in this application. Now I wanted to show you one other thing, and that's this file here called rectangle.cpp. We don't have to implement all of the functionality inside the header file like this, as you've seen. You are allowed, if you want, to implement it in here. However, when you do that, you have to call it by its full name, which is the name of the class and then that same scope resolution operator. Its full name, including the letter E. Once I do that, then in here, I change this from a definition to just a declaration. And if I build, this is quite happy to build, and it would run exactly the same. And you might do this if the header file was very, very large, or for some other reason that you wanted to keep the implementation of the function in just one file rather than in the header file. We are keeping everything mostly in one file today just so that we don't have to flip amongst as many files to show you around our demos.
Yep, but in very large projects that take a long time to compile, oftentimes making header files as small as possible and moving member functions into a separate file is generally done both to improve compile times but also to improve some level of encapsulation, because all those implementation details are now separated from the actual class itself, or most of them at least.
Even something as simple as sharing works amongst developers. Mm-hmm. If I wanted to work on the rectangle implementations, I could just check out the CPP file, and other developer who wanted to change something in the declaration of the class wouldn't need to care about that, what I'd done.
Yep. Cool. So finally, we're going to talk a bit about again about the const keyword and how it applies to objects. So, as we saw before in the previous section, we can const qualify integers. So here the int y is const qualified. We can't make changes to it. Similarly, we can do the same thing with rectangles or any class type. So here we have two rectangles. One of them is a mutable rectangle. We can change it. It's not const qualified. And one of them is an immutable rectangle. So it's const qualified. We're not able to change it. So this is simple enough, but we'll quickly run into problems. So for example, if we try to call the getArea function, it's not going to work. The compiler will actually complain, and we'll see that in a moment in a demo, I think. And the reason for this is that, so at first it might seem like, well, this doesn't make any sense. GetArea doesn't change the rectangle at all. Only the resize function changes it, but getArea only accesses the members. So the problem is the compiler doesn't know that. We actually have to tell the compiler, no, this member function is not going to change the object. And we do that by adding a const qualifier to the member function. So just like you can const qualify objects like ints and rectangles, you can const qualify member functions. And what this does is it says, I promise that this member function isn't going to make any changes to any of the members of the class. So for example, here we've made getArea const because it doesn't change anything, it just reads. And so once we make this change, now we can call getArea, no problem. So I'm going to now pass it back over to Kate.
Sure.
Who's got a demo.
I do.
I may have said we're going to demo something that we didn't have a demo prepared for.
So this is a smaller version of the same application. And what I'm going to do is first run it to make sure that it'll run and build and be happy. And I've just put the breakpoint on the very end because I don't actually care about the run. I just want to prove that it will run. But if I take these three rectangles and I decide to make this one value into a const rectangle, I can put the const here, or I can say const rectangle value, either way. Immediately these red wiggles appeared. And the hover over error is not that great. It says the object has type qualifiers that are not compatible with the member function. So let's do a build and look at the output. That's a little bit better. Not super great.
Yeah.
You can see, though, that the word const is in the error. And that's really the key. I'm taking value.area, and it's saying, wait, I bet you area changes value. And you said that it was const. Now, if we look at the code for area, you can see that it doesn't change the value in any way. It doesn't change the width, it doesn't change the height, so what the heck? But as you saw, the implementation for this function might not even be in the header file. And there has to be a way to tell the compiler, you know what, area does not change any of the member variables of rectangle. And that way is the const keyword. If I add the const keyword right here, why is he not happy?
Save.
Yeah.
Maybe.
There we go. A temporary thing from the... Now these wiggles have gone away. Now it's okay to call area on value again. Now I'm not calling get width and get height right now, so let's do that. Let's call values width, VW, is equal to value dot get height. No, not if we want the width. Get width. Same thing. I get an error because get width is not marked as const either. So we go in and we say, that's fine. Getting the width of a rectangle doesn't change any of the values. Getting the height doesn't. Now if I build, it succeeds. This is why it's so important to think about const at the beginning. Imagine if rectangle was an enormous class and no one had ever made a const rectangle, and then they suddenly had to go back in and mark all these methods as being const. They'd get irritated, and they really shouldn't. When you write rectangle for the first time, you go to say, oh, I'm just going to return the width. At that moment, you should be thinking, and I know that doesn't change the object, so I'm going to put this promise in here, just in case anyone ever wants to make const rectangles. Going back and adding it later can be really irritating, so you want to do it every chance you get. Now, of course, you can't do it here. Constructor changes the object, it initializes it. This version of rectangle doesn't have a resize, but resize isn't const either because it changes width and height.
And if we tried to make it const, the compiler would not be happy with
That's
us.
correct. You can't just randomly go around lying to the compiler. It will catch you. Thinking about const from the very beginning, that's absolutely vital to writing good classes and well-encapsulated code.
Cool.
Yeah.
Well, I think we've actually covered everything that, shockingly, that we were going to cover in this module. So, to go back over the, I guess the recap of what we were going to talk about, we said we were going to talk about objects. So we showed you how basically an object is, just a region of storage. So many people, if you ask them, well, what's an object in C++, they'll tell you, oh, it's an instance of a class, or it's a thing, this advanced thing. But it's not. In C++, even ints are objects, even though they don't have member functions. Like, not all objects are of the same kind of thing. So we've seen how you can define your own types, like our rectangle class. You can define higher order types or higher level types to describe them. We've shown how you can initialize things and encapsulate your data to make your code easier to understand, easier to debug, easier to use your reusable types. And then we've seen how the const qualifier works together with things. So,
absolutely.
All right. So I think we're going to take a meal break now for 1 hour, and we will see you after that.